So the next speaker is Brian Host. He's topic is calibrating a network analyzer. And Brian's biography.
He was born and raised in Tokyo, Japan, to a Japanese mother and a Chinese father, with his nationality being Japanese and South African. He's fluent in both English and Japanese, and English being his first language. Brian moved to Texas to study at LeTourneau University in 2007 to pursue his electrical engineering degree. Brian moved to Michigan after graduating from university in 2012. He is now based in Farmington Hills. Brian previously worked at an antenna manufacturer for 7 years before moving to Keysight. He worked on validation as well as R&D, design, and simulation for antenna products. Brian.
Thank you. Thank you, Scott. Good evening, everybody. Thank you. That was a clap started by my own coworker, so that's a little biased, but don't mind him. Thank you so much for your time. I appreciate your opportunity to talk to you about VNAs and the calibration of fixtures. I really appreciate that. So just to begin with, this is the agenda that we're going to talk to about. Today, we're assuming that you guys understand what VNAs are as a concept and understand basic calibration techniques. Our focus is on the fixture, how to get rid of fixtures, because we can calibrate. But if you want this discussion, please contact us, because Keysight does have a online, in-person as well, seminar we can give that's related to VNAs, network analyzers, and calibration. So if you are interested in learning more about VNAs and something that we haven't discussed today, please contact myself or Blake, who's in the back right there. So feel free to email me as well, and we'll be here to support you. Anyway, so today we're going to talk about some background of fixture removal, some of the simple fixes, calibration techniques. These are calibration techniques with the fixture, not calibrating the system. So just a clarification, de-embedding techniques, some of the results of the de-embedding techniques. We're going to talk about Keysight automatic fixture removal. And lastly, we're going to touch on analyze software, our Keysight physical layer test solution. So some of the measurement challenges we're having nowadays. So nowadays, a lot of the things that we get are needing to be characterized by the VNA. And some of these connectors aren't connectors that we are able to connect with coaxially. So the large challenges is the boards are getting smaller, your fixtures are getting smaller, your connectors are getting smaller, your connectors aren't coaxial. So how do you get rid of them? So that's kind of what we're going to discuss today and the ideas that we're going to talk about. So why do we want to remove the fixture? So we use a fixture to connect to our devices. So previously you saw the USB, we use a fixture to connect to that. So why do we want to remove it? Well, the reason why we want to remove it is because we want to actually measure the device and understand the characteristics of the device without the fixture, especially with higher frequencies and how much we have to deal with those things. It's getting harder and harder to neglect the fixture effect on things. Another one is more model correlation, excuse me, as well as reduce overall test time. So before we start, we're going to use the term reference plane. So what do we mean by reference plane? Well, a reference plane is where the measurement system defines the measurement as 0 amplitude and 0 phase. So an example is, if you can see here, we have the PNA, which is our Keysight's network analyzer. And then down here, you see the cables on the left and the right. That's a cable. At the bottom, you can see that ECAL, TRL, and SLT reference plane. So this is where we typically calibrate our cables out before we start any measurement. Now, with the addition of fixture, we're adding fixtures and a DUT. The reference plane that we want, ideally, is to move it from the end of this cable to right where the DUT is, because there is length associated to this. There is loss associated, and this can end up giving you either false negative or false positive. So it's very important nowadays to understand that. So that being said, now we kind of defined the parameters of what a reference plane is. I'm going to give you a quick overview of some of the techniques that we'll be using discussing. So here you can see the chart that's broken up in two sections: direct measurement, and modeling. And even within that, there's sections. There's an easier method of implementation, and there's a harder method of implementation. Now, with the easier method of implementation, it's easy, but the accuracy is a lot lower. But with the higher implementation, the more time it takes, the more hard it is, the more higher accuracy we can get. For example, for direct measurement, Normalization, for example, zeroing out a cable. That's very easy to do, but it's very prone to error because it's only one factor that you're doing versus a full short open load through measurement where it's characterizing all the fixtures, the phase, the amplitude as well. Also, on the other hand, is modeling, modeling port extension where we're virtually extending the port, we're changing the electrical delay. Or de-embedding where we actually use the characteristic S parameters of the fixture to understand the properties and de-embedding it, removing it from the fixture. So this is just a general overview. As you can see, we'll touch on a lot of these topics throughout the presentation, but just to give you an overview, there's different levels of fixture removal and different levels of easiness of how to implement it. So here's some of the background and simple fixes of. So the first one is what I discussed is normalization, where we take, for example, a cable and we normalize the loss through it, a single factor, whether it's a length or loss. It's very easy to do, and it's usually just a memory thing. So you just clear out memory. So it's like resetting something to a certain point. The only disadvantage, it's only single term. So if you have a cable, you're looking at the loss of the cable. You're not really necessarily calibrating out the phase because the cable, there's a phase involved. And another thing is when you change the frequency, it's not valid anymore. So anything, it's really frequency dependent on that section. Another one's time gating. What is time gating? Well, time gating is taking the frequency division, frequency measurements and changing it to a time domain. And from the time domain, we can actually gate out where we can take a certain time, whether it's before a certain area to let it in or after to let it out. So it all depends on, this is one method. The advantages, it's really quick to see where a fixture is, but it's more of a reference because if you were to use this from an eyeballing standpoint, eyeballing is not the greatest because we're trying to figure out where the impedance mismatches in the time. So this is one way of doing it as well. All right, so far so good, I guess. We'll move on to the next one. So one thing to note, I'm going through different phases from easy to harder. So we're starting with the more easier, less accurate models. And then we're going to move on to more complex models towards the end so that we can at least get a groundwork. So if this is review for you, please be patient. This might be nice to easy class for you guys. So just give us a couple minutes to set. But anyway, the next one is offset. So what is an offset? Well, we manually offset an amplitude, phase, or electrical delay. This is where we change physically where it is. So one way to do this is, well, if you know the characteristics of the delay, for example, your electrical delay is a certain length, then you can input it. But obviously there's no reference to check it against. It's really just your knowledge and put it in. So there is some flaws in this. It is very easy to do. So again, it's easy to do if you're using it for. We'll get there. So let me finish this, and then we'll go to port extension, then automatic port extension, and then de-embedding. So give it a little bit of a second. So so from here, this is where we can actually put it in and change it manually. So the advantage, again, it's easy, extremely easy to use, no standard necessary. Available VNAs that are fairly old. So any VNA, not only the ones that we have out here today, but any VNAs would have this function. Again, it's very prone to error. As you can see, it's one, you can have nothing to base it upon. You're using values that someone gives to you. And it's good, but you also have to trust in the person that you get it from. So anyway, moving on. Port extension. So this is port extension again. This port extension is the difference between this and that is these are separate line items. You can see the electrical delay is just changing the delay. The phase off is changing the phase from, if it's usually when a zero phase, you're changing the phase, so it offset the phase it's at. Magnitude is magnitude of what's coming out. It's separate ones. Port extension essentially is the same thing, but we have it all in one setting where we can do it. What thing is handy is for the delay, we can add the time, electrical delay, which if you don't know the electrical delay, you know the board length, you can put the board length thing and it'll convert it to electrical delay or vice versa. Another one is the velocity factor. You can change that. One cool thing is the loss. We can actually import one thing that is different between putting it in. We can actually use a calculation to calculate a loss, whether it's one port of reference or 2 ports of reference. I didn't put the calculation how the loss factor is corrected because it's a little bit too detailed, I think. But the fact is that with the previous one, you have to have the values. With this, there's some calculation that can be done in this mode. So if you want to do port extension, you can obviously put it in here manually if you want to. Like you can see here, there's a distance, there's offset, but with this, it adds a calculation that you can do it automatically for you. So it's a little bit of ease to that as well. So this actually goes into the next topic, which is automatic port extension. It's exactly the same thing conceptually as port extension, but it's a mode that helps your life easier. And these are things that Keysight does with our VNAs. Keep in mind that these are the techniques that we do with Keysight, and I'm sure some of the other vendors do have similar de-embedding techniques, but this is based off Keysight modes. So the advantages, again, it's extremely easy to use. We can plug it in. Like I said, if you have the delay or time, you can plug it in, it'll automatically calculate it for you. If you have a loss, you can add the loss as well. Or if you have 2 points of loss, you can use that and it'll calculate the loss. One thing to note that this is prone to error and there's no standards to verify it as well. And it's error associated with linearity. So that's one thing to keep out in mind. So now, what if you don't have any of these measurements? You don't know the distance, you don't know the velocity. Well, Keysight has a mode where we have called automatic fixture removal or port extension, automatic port extension, where we apply both the electrical delay as well as insertion loss to the measurements, and it gives us a very good de-embedding of it. So I'll explain how it does it. So how it works is same as port extension. We're looking at the same variables. So insertion loss, so loss, as well as let's see, same as loss is delay or electrical delay. So we're doing the same meters. So what we're looking for is the same, but it does it automatically. So you don't have to have a spec sheet to do it. You can plug in your fixture and it'll automatically do these calculations. So what it does, so what we'll do is how it works is you calibrate out your VNA cables, test cables, and you'll still have to calibrate this fixture that you're putting as part of the VNA. So once you finish calibrating out, the reference calibration plane is right here. We want to move the reference plane to this point where we have the device. So what we're going to do is after this measured, we'll connect the cables and we'll measure an open. Why an open? Well, open, we can use that to measure a through. We can measure your loss, your return loss, and we can measure the delay, electrical delay as well. So it does it automatically for you and also looks in the time domain as well. So that takes care of that. So let's move it. So this is ideal for applications where you don't have a through or anything. You can just use an open or short. So it's very handy to use and it does a lot of things for you. So if you have a program that if you don't have a spec sheet in front of you and you just have a fixture, you can actually de-embed it without that because it'll find out the parameters that you need for that application. So one thing that it doesn't do is the mismatch, doesn't fully correct for mismatch, and loss probably has to have a linear response. And the number of standard nested depends on the bandwidth of the device. So obviously, if the bandwidth is, if you're thinking big bandwidth, time domain, you can get smaller measurements. So it all depends on that as well. Any questions so far, or so far so good?
Why it opens with just from my own experience, I've used it, I've done manual sorting.
Yeah.
And it tends to be the short tends to be a little bit better to find than electrical open.
Well, we can talk about, I didn't put any of that reasoning behind these slides. So if you want, let's talk about this on a sidebar because I do have that as a different topic of discussion, but just as a, we can also debate through as well, right? Why isn't there not through? But because through is actually the preferred one as well, TRL measurement. So it depends on what you're doing as well. So we can talk about that a little bit in detail as somebody wants to understand that, but I don't have the slides ready for that here. So we'll step into the calibration technique next. Now, to this point, this is calibration technique, not calibrating the VNA cables. This is calibration of the fixture. So once we calibrated out the cables, we have the fixtures on it, and now we're trying to calibrate using a cal kit of some sorts to de-bend the fixture. So this is a fixture made by the fixture vendor with different open short load, different calibration methodology. So we'll talk about that. Just to let you know, this is not the calibration system, it's calibrating out the fixture once the calibration of the system is done. So the first method is your typical SOLT, short open load through. And just a quick reminder how many different things you have to do. If it's a 2-port, this is just a 2-port, just as an example. You have a response through, which is measurement of the through loss. And you have a 1-port, which is open short load. And if you have a 2-port, you have a total of 12 different measurements you have to do. So this can be quite a tedious process, but this is one of the methods people do use. If there is a calibration fixture, they sometimes add a calibration of this with these calibration standards. So just to let you know, these are some of the calibration that has to be done. One of the things that to note is if you do end up making a cal kit for a certain fixture, you have to use the same PCB board as the fixture because of the fact that the PCB variants will change. And that's one of the things that to note, that if you're to do this, it has to be the same PCB board. So there is some complexity, but designing is not hard, but there's some minute details that you have to keep your head on. So this is showing you some of the mechanical actual measurements. So what about modeling? So if we were to model, the simplest term, it would be this for open short load term, but it's harder to do that with modeling because the load is a lot dependent on the frequency. So if you have a low 50 ohm load, it's usually a frequency bound thing. So it's harder to do that versus open or short, where modeling is a lot easier. That being said, that is one of the bigger flaws of this, is because of the fact that it is frequency dependent in certain de-embedding or calibration factors, that it's not really recommended past 1 gigahertz to do this type of method of open short load because of the fact that there is some loss associated with that. And it's also hard to build a broadband termination in most fixtures. So because of fact, sometimes there is certain megahertz to gigahertz. A lot of people look at 3 gigahertz sometimes, and that broadband cannot be supported. So keep in mind that when you try to use this as a de-embedding method. Another one is TRL, through, reflect, and lines. It's usually a more suggested way of doing this, where we have multiple calibrations throughs. We have what's called 2x through, where we can measure, divide that in half mathematically to figure out a through. We also have a short and open and different lines of length. So the different lines of length will be measured, and from that measurement, we'll deduce the fixture from it. So again, this is ideally, oh, sorry, this is a quick reminder. We want to move the TRL reference to this. So we are measuring different throughs and different things. We also have, as part of the reference, sometimes they have a through with the DUT inside of it, so they can measure it to de-embed it better. The advantages is open and short models aren't required. You just need a through measurement. It's fairly simple to build and characterize. A lot of times it's preferred over SLT because SLT, again, it's frequency dependent, frequency bound. One cool thing about this is this can be implemented with other de-embedding techniques, and it can morph into different de-embedding, different de-embedding methodologies. So TRM, RLL, RLM can be used for both low and high. So that's one of the bigger advantages of this using versus the SLT methodology. So one of the things is disadvantages non-matching standards per port can be an issue with constant performance. And consistency between line standard impedance can cause step and return loss data. Consistency between line standard will add measurement uncertainty, and TRL kit not matching fixture will add uncertainty. So it's important to have a really matched circuit. A lot of times this also is recommended to be similar, built on the similar board as what you made the fixtures, so that it can be similar. So we talked about the mechanically hand actually measuring techniques where you measured either a fixture, TRL measurements or some sort of measurement. But now we're going to go into de-embedding, which is more modeling based type of things. So de-embedding, a lot of this is based off simulation. So a lot of simulators, Keysight has a simulator as well. We have simulator tools, but with those simulator tools, if you build out a fixture, you can also characterize and get S parameters from that. And with those S parameters, we can do a lot of different de-embedding techniques with it. So one of the de-embedding techniques that we do is what we call a 2x through embedded, where we have a through, where we have the two fixtures put together, and we measure the through across it, and we'll divide it in half, split it in half. So that assumes, again, that these fixtures are exactly the same, right? The left and right have to be exactly the same, but that's traditionally with what we call AFR, automatic fixture remover, which is a Keysight de-embedding technique. It doesn't matter if it's, excuse me, it's the same on left or right, but traditionally with the methodology is to divide it in half and then measure it. So it has to be the same. Another one is using the reflect or short. And one thing to know that you must not have it radiate, because if it does radiate, then everything changes, because radiation does change things around you. So an open must not radiate. So one thing to note that it is slightly less accurate than the through, and we'll show you a quick later in AFR, we'll show you a little graph to show the difference, but it's pretty close to each other. Ideally, a through is what's looked for mostly as a standard, but open and short is a new method that is quite accurate too. So once you have that de-embedded, you can add that to your VNA measurements. So if you have a Keysight VNA, you could take that model, S/m model, de-embedded structure, put it in there as a fixture, and it'll de-embed it for you. Or you can use what we call our Keysight physical layer test system, which is our PLTS software, where we can take a fixture or the S parameter of the device and de-embed it in software. So what that gives you the opportunity to do is, if this customer gives you measure a cable, but you don't have the fixture that's holding the cable, but the customer sends you the S parameter for that, you can de-embed that later. It doesn't have to be right now, right then when you're doing the measurement. So this is, because it's software based, it's very handy to be able to do that de-embedding analysis afterward. And we'll talk about a little bit about the PLTS software as well, a little bit, to give you an idea what I'm talking about. So these are some results. To talk about the results, I mean, what you would expect to see if you did a decent or good picture removal. So one of the concerns is we want to always make sure that our fixture is always given the same results, same thing. So one of the things is make sure you have a good fixture, make sure you have a good measurement of your fixture, make sure you have a good S parameter de-embedding of your fixture before you do anything, because if you use a very bad modeling, you're going to get modeling that's horrible out as well. So whatever you use, make sure you have a good modeled, whether it's from the results you have, the S parameter results, make sure you have good measurement results, or make sure you have a good de-embedding model before you go further. Because if you go further with bad things, your model will cause bad results. So this is just an example of, I don't know if you can see, this is just an example of a fixture removal. We're using automatic report extension for this, just to show you. So here you can see a coaxial cable. This is, we're just looking at reflection. We're looking at the time here, and then we're looking at time as well. So we're going to look at the time here first. You can see this is the blue line is the original blue line, and you can see here there's impedance mismatch. That is probably the connector that we're looking at, and the red is the de-embedded portion, which includes the connector. So if you can look at the red, you can see notice that this divot is in the negative time. So what it did is shifted it away from positive. So we're not even looking at considering this as part of the measurement. So you can see that de-embedded this out of the equation, so that now we know that we're directly looking at the unit, not the fixture. And here you can see also the return loss here. The red is the automatic fixture removal, the automatic port extension. The blue is without it. And you can see that you have a higher value because there's more insertion loss with the blue with the fixture involved. So that's an example of what some things you can look at to say, okay, it makes sense. Understanding here, I guess. So there he is. What I was saying is this is removed because it's pushed out in time. So these are some of the things that you can look at to see if your fixture is good in a sense, or you need to redo the fixture. Again, there's other methodologies of testing it to understand if, but this is a good quick check to understand if you did the thing right. Again, here's some more things that you can see here. We got rid of that as well as you can see that we clean it up on the other side where the fixture is. We got rid of that in the time domain. So any questions so far? Pretty clear or vague?
The audience, you want it now or?
Sure.
Okay. This is from Joanna McClellan. Many semi-rigid cables have dielectrics that expand when heated. This will change the Z0 of the cable. How would you suggest moving the calibration plane to the end of the cut semi-rigid cable pigtail?
No, I'm just trying to think. So essentially they're saying is they have a test cable and then they have a semi-rigid connected to the test cable. And they want to make sure the test cable plane is moved to that one point and that test cable is heated, that they said, right? Or the measurement.
It says rigid cables have dielectrics that expand when heated. This changes the Z0 of the cable. How would you suggest moving the calibration plane to the end of the semi-cut rigid cable pigtail?
I'll come back to that afterwards. Let me give you some time to think about it.
Oh, here's a response. You take a cable in tow to make two pigtails. It'd be nice to have TWO. Anyway, Joanna, if you can maybe send a photo or a diagram, would be helpful too.
I will think about it and I will try to respond to that after once it comes to my mind. It might come halfway through. Okay, cool. If anything else, we're going to go to the next level of modeling that we have. And this is what Keysight's automatic fixture removal. This is a technology that Keysight has and currently uses for a lot of fixture removal, and it's AFR for short. And I mixed up saying AFR and APE, automatic port extension, a couple of times. Apologize for that. So with the traditional methods, it's a lot of these fixtures that we have, it's hard to connect directly with a coaxial one. So a lot of times you need to use a probe device, and these probe devices can be very expensive and very complex. This is just an example, wafer probe, and you can see can be complex and pretty hard to de-embed the whole things. But we're not going to focus on that. We're going to focus on how we can de-embed this in software so that we can avoid doing this and do it a lot easier and it'd be a lot cheaper too in the end. So historically, we talked about this in the de-embedding where we do modeling as well as the traditional TRL, the through reflect lines, where we do the modeling of the left half and right half where we cut it into half. That's a traditional method. But with that, a lot of times with the TRL method, it gets very complex, right? This is just for a single-ended where we have one through, one line, two lines, one line open in DUT. And you got to do that for a certain frequency, for a measurement. It can be confusing. It can be hard to characterize. But now imagine that, because we're now talking about differential pairs where you have to take two cables and treat it as one. So it's going to be very hard to create a fixture or a line that can be identical across this line as well as the other way, because not only you're concerned about one cable and one fixture, you have to make four of these connectors and two of these cables exactly the same to make sure it works. So it's very complicated, but that's why we introduce AFR, automatic fixture removal, where instead of using the TRL modeling, we're going to use the through, differential through, and open that we talked about in de-embedding previously we referenced. So we're going to use those modeling instead of this method to make things easier. And we'll explain some things later. So we'll talk about the first method, with the through method. So this method is again similar, where we have a device, fixture A, fixture B, we have the DUT, and we're just going to measure the through. The idea is we're going to mathematically divide in half, and we're also use time domain to figure out where the fixture is. So that's why it doesn't really matter if there's a little bit of an impedance mismatch between the model, because we do use time domain to make sure that we can see where things are. So some of the limitations and the advantage to this method is the left and right have to be the same delay, but the launch, the fixtures, the launch, the connectors don't have to be matched. As I mentioned before, because we're using the time domain, traditionally, everything has to be matched. But since we're using time domain as well, we don't have to have this part matched. We're just going to have the lines and cables the same, and we just divide it in half. One other thing is the requirement for the fixture has to be 4 times the pulse rate of the system rise time, because we're looking at time domain as well. So we have to get a certain amount of measurements for that. So when you do the measurement, you have to think about that, your bandwidth, right? Because if in time domain, the bigger bandwidth, in the frequency domain, you have the smaller pulse width. So one of the things, if you have a very small fixture, you have to consider a very wide bandwidth. So that's one thing to also consider. So especially with the fact that you need to have 4 times the pulse width. So if it's a very small one, you have to have a very big bandwidth so to get that forward. So that's one thing that we do. And the through cannot be too long. The band should be higher than DET bandwidth. So yeah, there's some disadvantages to this, but it's a very handy way to do it. So the other one is what we call one port AFR. So why is this handy? Well, one thing is we can use this for probes, right? Because a probe doesn't have more than one port. So it's a very handy way to de-embed a probe. So how does it do this? Well, we measure an open and short with a VNA, and we mathematically extract S parameters from the open and short. And we use that with the time domain. If we have all the S parameters, we convert that to time domain. We can figure out where in time domain fixture is, and we can use that data to help us de-embed the fixture. So again, it's very good, very useful. So if you have a probe, very useful for a probe. So you don't have to do a through, you just use an open or short. Pretty easy standards to do. So here are some limitations and things to, again, no radiation. You shouldn't radiate, because if you do radiate, it's a whole nother, you guys are EMC people, you know what happens when things radiate. So we want to avoid radiation in that sense. So we want a good reflect, and again, the length should be 4 times. So there's certain things that you should consider. Like I said, before anything you do, it's always good to sit down and write down what you're going to measure, how you're going to measure. So they have the parameters out and understand, okay, if I have to have this picosecond rise time to be 4 times the length of this, then I need to have this bandwidth. So one thing that I wanted to stress also is that please sit down and understand the parameters you want to do before you try to jump into de-embedding, because if you jump in this without understanding what you're trying to measure, what bandwidth you're looking at, what you're looking at, things can go wrong quickly, and bad de-embedding of a fixture can result in very bad results. So one thing I want to make sure that you know is, especially for that point. So here's the example that I'm going to show you with the difference between open and short. So we're going to use this Rogers PCB just to show you an example of the open and short. So here's an example of the difference. I don't know if you can see fixture with a through and open. As you can see, the higher frequency it goes, there is a little bit of difference, but for the most part, it is really close to what we're looking at. So if you look at the difference here, this is a through, the blue is a through, the open is the red, the green is with the fixture. As you see the fixtures, without the fixture, you have the issue with the start and the finish of the fixture. And this is the measurement. So as you can see that the open and through has de-embedded the start and finish, and you can see that even how close it is to one another. I think compound, let's see, here it is. So you can see that the difference is quite small, minute, and I think 0.1 or 0.2 dB is usually acceptable in terms of differences. So another thing is interesting is we talked about how we have to have everything symmetrical. This left side has to be to the right, but we have a method in AFR to do asymmetry. And there's 3 methods of doing asymmetry in our methodology. The first method is, if you look at here, there's a fixture. There's the fixture A is different color from fixture B, signifies different fixtures. The first one we'll do a through, 2x through, where we take the through of each one, divide in half, and then we do another one for this one, divide in half, and we can de-embed each of the ports separately so that you don't have to worry about having to be the same. That's one method of doing it. Another method of doing it is to do an open and the second open. So same method, but instead of doing a through, we're doing an open. But there's a third method also, And the reason why we do the third method is that we want to eliminate any reflections or anything that's outside the bound of an open. So if there's something that's reflecting or anything, we use the through to make sure there's nothing in it. So these are all valid methods to use, but then this is the most accurate method so that we can avoid anything, even with a mismatch. Oops, sorry. So it's a very handy tool. This is done mathematically, so I don't have to do it, luckily, which I'm not really good at math, but it's quite easy to do. So another one is bandpass AFR, where we use a bandpass to measure. So we can use a bandpass to figure where the fixture is, and we can negate it out. So that's another methodology. And so one of the questions people ask, so how about if the impedance is off? What if I'm using a 50 ohms system and then the system is 75? Well, it's not that hard. It's just a different way to see it. Can we use a 50 ohm VNA calculate to measure a DUT at non-50 ohms? Yes, we can. It's just internally, it takes care of itself. So it's not a problem of if, it's just making sure you have the right setting set and know what your impedance is, and it can shift the impedance for you. So this really covers a lot, right? Because traditionally with de-embedding, everything has to be perfect. If you have a 50 ohm system, it has to be 50 ohms. If you have a cable, everything has to be the same. But with improvements of how we learn de-embedding and then how we are able to correlate different models, we're able to do this more and more, where we can use just a simple, open or short without having to do everything. But the one thing that I want to stress is every calibration, this is the end of the basic calibration methodology, but one thing I want to stress is with each de-embedding, or fixture removal, there's advantages and disadvantages. And each advantage and advantage is not for everyone, right? So for example, if I am on the field and I want to check something, and for something reason, something's not working right, and I just need a quick check. Maybe, a normalization of the cables is more than enough, right? Or even a port extension, because I need something on the fly and need something accurate. I need something that's more if it's there or not. But then there's people who need to de-embed fixtures for automotive Ethernet, where there's a lot of noise, there's a lot of things, a lot of cables. So then you need a bigger, better fixture de-embedding technique, which understands not only from frequency domain, but also the time domain. So it really depends on what model you're using, what model fixture you're using, and what kind of the end goal your modeling is supposed to do. So we gave you today a broad set of kind of basic tools. There's a lot of other things that can happen. There's a lot of ways to do it. But this is a basic starting point. So once you understand some of these methodologies, you can understand other methodologies that are similar or slightly different. So really, it's up to you guys to understand that there are different ways, and understanding what your end goal is and what you want to do will define what it is. So maybe today port extension is not it for you, but maybe you want more complex and automatic fixture removal is for you. So if you have any questions regarding which type of fixture removal is better for you, we can talk about it. And one of the questions was that hopefully I can answer that today. If not, my email is here. But before we go further, one of the things I want to talk about is our PLTS, our physical layer test solution. This is our solution that does a lot of data analysis and it's very helpful. So as you can see, this is a quick overview of what it can do. Here is our software. As you can see, there's a lot of things going on. You can see there's S parameters, you can see Smith chart, you can see time domain, you can even see an eye diagram. Not everybody uses an eye diagram, but it can do an eye diagram. It can generate a bit pattern. So one of the cool things is this is analysis software. It can analyze if you have S parameters or data, it can plug it in and it can do all post analysis for it. So even TDR, frequency. But the one thing I wanted to show you is, so complete characterization, time domain, frequency domain, differential. You can do common mode, single-ended. So if you're doing EM for cables, common mode conversion, you want to see that, you can do that as well. But this is showing only a 4-port, but we can go up to 32 ports. So if you're a cable maker that wants to see noise or something across the lines and want to characterize all 32 all at once, we can do that as long as we have the S parameters for all 32 ports. It can do it. And as I said, it can do an eye diagram where we can generate a bit pattern, and we can simulate a bit pattern and try that from your S parameters. So if your S parameters can do that. So one of the things that the main reason I wanted to bring this up is that we can do a lot of different types of de-embedding through this. So as long as you characterize your fixture and have that characterization, we can de-embed it however way we want with our de-embedding software. So today we did AFR, automatic fixture removal. We can do that. So as long as you have S parameters. So this is a very handy tool that we have that you can use it as a post-production. So if somebody says, hey, here's cables, here's a fixture, measure it today. You measure it, I need a fixture removal. You don't have to have them send you, remeasure it the spot. You can just send you the S parameters. And once you have the S parameters, de-embed this post-production. And once you have the S parameters, you can measure it, and then just de-embed it later on. So this is a powerful tool, in my opinion, to help you organize your fixtures as well as data, but also help you get things easier and faster. So one of the quick tools that we have, and that's thank you, which means end is the end. Hopefully I wasn't too vague, or hopefully I wasn't too quick about anything. Q&A session. I know I have a lot of time left, 10 minutes-ish. So not a lot of time, but if you have any questions, please let me know. I know there's some online that are on. Let's see. Oh, I understand. Okay. Well, that's all. So I don't know if you can do anything. So I looked at her question. The question was, let's see. So essentially, the question is she wants to know how to de-embed a pigtail, which is what a pigtail is. It's a cable that you cut in half or cut it. You have the center core and the ground, and you use that to connect to a part and use that as a pigtail or jump off point. And I'm assuming that's what she's asking, how to calibrate. And she's saying that her question is the center core of a cable will expand and change with heat. And if you know anything about cables, if the diameter of the cable changes, that changes the impedance. The impedance calculation of a cable is done by the core, insulation, and the dielectric distance. Good question. I don't know if we can do anything about the heat itself, because that's something that's changing. But honestly, I would say either a port extension, automatic port extension, which looks at the insertion loss of that, or I would always go with automatic fixture removal just because it looks into the time domain as well. But actually, automatic fixture will be better because it's looking at the time domain as well, despite having the expansion of. Yeah, my personal opinion, the way that automatic fixture removal is that it does it automatically for you, but you can also adjust where the time domain is. So if there is a heat expansion and you see an impedance mismatch, maybe you can change that to where that is. So there's an option that you can change that, or you can use port extension with as long as ideally if you don't bend it. But
now I know you have your P&A expert, and you have like for a flat panel display 3 or 4, there's a source current on the bias field injector. So you're injecting the current power to stay in the panel.
okay.
You're testing it. You do have the current source because normally you're testing pretty low power, but if you're doing a bias source on your camera, which doesn't happen,
Yeah.
then you're going to be sourcing current from the other current. So you now know the current, and you might have stumbled getting the heat out of what's going on the cable. You know what current size.
Would you like to present today? This is beyond me. This is beyond me. I'm sorry.
How can I deal with, okay?
Yeah.
Probably deals.
From there are ways to do this, but from my standpoint, with the embedding methodologies. No, I agree.
A lower down this thing?
Well, I think she's saying that when she solders it, it expands.
Well, maybe it's an engine compartment, so you check it at room temperature, and you put an engine compartment, and you got something different.
Well, then it becomes a different.
Right.
it's-
Well, the pigtail thing, back to that, and same with the fixture, you should be able to time domain zero out.
Yeah, you should. So as long so that's why I'm saying either use an automatic port extension or use and supplement time domain just to look and understand where the electrical delay is. So you could do that, probably supplement time domain gating or looking at where the electrical distance is, and then you can do a port extension and use that as supplement to make sure that you know where exactly the end of the cable is.
The other thing is put the cable in a temp humidity oven and then.
Yeah.
Test it.
Yeah, you can do that as well. You can also, that's somebody who does temp testing for you. That's also to normalize the fixture and the cable before you measure it would be then a good idea as well, if you want to do that. So a unique example, but I guess, yeah, you can do that.
Says the diameter of the cable is not just the soft electric, which is out of the cable. Oh. Get Teflon.
Yeah, I'm trying to think, but not sure off the top of my head. But yeah, electrical delay plus, port extension, maybe using time domain as a supplement would be good, I think, to de-embed that. Any other questions or any?
Any of these techniques are going to assume time invariant. In other words, the parameters aren't shifting over time. Because if they do,
Yes. Obviously, yeah, because again, normalizing your equipment would be I assume normalizing your equipment will be normal, especially your cables, your fixtures and everything. Since it's in time, it will affect it if you don't normalize it, as you said, so. Yeah, I get it. Anything? I mean, it all depends on the application, right? Any questions? Any comments? No fruit was thrown at me, so that's good.
When you're using this, you said like on automotive Ethernet. Now, the wiring for the automotive Ethernet, maybe you can assume it's perfectly matched or something you would play in all its characteristics, but rare to have where it can actually cut at the same. They're not exactly the same. You actually use them stuff.
The DM twisted pair.
Yes, if you said twisted pair index.
Okay.
Automotive Ethernet.
Yes.
And that's.
You're asking me if I use AFR?
Yeah.
Perfect. Let me just. Are we? So Scott, I guess I put it back to you if there's anything.
Well, let's do the drawing. Okay. You want to step there and I'll feed you numbers.
Sure.
Okay. So anyway, there's this question here. Did you guys go listening yet? No. Bring up your questionnaires.
I'm gonna put myself on mute, I guess.
This is gonna take a while though from the filling zone. So maybe we should stop the
Zoom. I think if anyone else has questions, please let me know. I think we're gonna stop sharing.